Okay. Wow, it was interesting talk. So, I do agree with Lauren that we should not fall in love with our models and our hypotheses. What we have to do once you build up a model or hypothesis, you have to try to destroy it first. And also, I think that the models and hypotheses are built up not because we know everything, not because we know exactly how it works, but just in order to understand how the things work. And also the models are built up usually to answer the questions. So, since the dawn of time of humanity, there is a scientific way of doing things. So you have observation. After observation, you build hypotheses. You provide some sort of experiments, and you destroy your model, or you build a new one. That's how the science usually works. So, let me start today. So I will try to talk today exactly on the questions which just before a few minutes was pointed out. If we look all the life forms and see that if we analyze all the life forms, we see that we have approximately 300 common genes and approximately 52 protein domains. And of course, that's why we know that Luca exists, our last universal common ancestor. It's reasonable because of this data. Now, if we try, and many scientists did so far, maybe thousands of papers which analyze the top-bottom approach, top-down approach, and ask what are the very first structures in biology that we can figure it out by this approach. Of course, top-down approach has its own limitations, but based on many data, we will see that the first protein domains are those which are nucleotide binding domains, thanks to the research of Gustav Anolis. And also the very first protein domains are not binding domains. The very first RNA structures are PTC from the large, this is the peptidase transfer domain center from the large subunits of the ribosome. Also some helices where is the A sides of the small subunits of the ribosome. And this is also thanks to the research of Warren Williams that he just taught. And also we know that the tRNA is among the very first emerged in life. Now, if we look from bottom-up approach in prebiotic chemistry, actually the entire symposium today is for this, most of this. So I'm not going to repeat everything that was done so far and say. But we can reasonably assume, based on many experiments, that the amino acids was around and nucleotides also around. We just was listening to talk of John Sutherland. And of course, it's extremely reasonable to assume that some short RNAs are around. Now, it is very clear for everyone in the room here that origin of life is somewhere between this, between those two. And the major question is, how did it happen? Now, think about it. If you look these structures, these domains, those domains are a result of a long evolutionary pathway. This is a complicated structures. The first protein domains are a result of evolution. Some sort of selection was applied for a long period of time. And we also have to understand that nothing complicated could happen without selection and without evolution. Therefore, if you have some structure which is relatively small and have interactions, this structure, in order to evolve, needs evolutionary pathway, needs selection. And I'm calling it information-dependent selection. So, let's try to answer the questions which I just listened a few minutes ago. So, what is the mechanism of information-dependent selection? How the Darwinian evolution works? So, how biology goes from disorder to order, or from positive entropy to negative entropy? I mean, this is absolutely fabulous questions. What are the nuts and bolts, the mechanisms which actually do that in biology? Okay. Now, if we have informational source which determines it's some kind of structural function, and those interact to each other, and you have this system. If you put this system in environment, what could happen? Two things could happen. One thing, this system simply would perish. It will be destroyed from the environment. But also there is another possibility where this system would survive. And why this system will survive? The reason is simple, because this structural component, the structural component and function, actually protects the entire system, protects its own information source. And if you think about, if something happened in the informational source, some kind of changes, because there is a specific rule, how you define, how you execute the function in the structure, of course, the changes in information also will reflect directly the function in the structure as well. And you have again the same situation in environment where either will be beneficial these changes or not be beneficial. It is absolutely clear that this is exactly the mechanism how Darwinian evolution works. And we know that. But this is the minimum system, the very minimum system by which we have to look for in origin of life. Therefore, we can say that Darwinian evolution is a dynamically stable system where an information determines its own supporting structure. It's simple as that. Now, anything, you can have some kind of periodic interactions with many different polymers or moleculars and so on. But you cannot be able to evolve. You cannot make anything more complicated, more than, for example, 6, 7 specific amino acid or nucleotides, without having this specific, without having this specific feedback. At the moment when this feedback is established, the system now can evolve. But for this moment, all of the interactions that could happen, all of these interactions will happen in the same way with the same identical probability every time, and nothing more will happen. You may have extremely cool, interesting interactions which are resembling many things, but without this positive feedback, you're going to nowhere in terms of advancing of this structure. On contrary, once you have this feedback from the structure and function to the information, now this system is capable to evolve. And you can continue, and every single time you may have more advanced structure. This is the way how the life is built up. This is the way how it goes from chaos to order. And also, look at that particular sentence here. It's not bound to any material specific, big or small. It is just simply describe a principle of working. So we are not obliged here for RNA or peptides. We are not obliged in this particular way of something complicated or not. This system could be extremely complicated, as we know, and this system could be extremely simple also. One thing is important, the capability to evolve. And this is the recipe for anyone that wants to build artificial life, for example. Use this formula. Also, if you go in another planet and try to look in, and you see some interesting interaction between some primordial polymers and so on, just look. Is this particular primordial interaction fit in this system? If you find in another planet the same type of interactions, obviously these interactions goes to advance. They're in a pathway of evolution. One thing we should be aware in this situation, and this is a situation where you cannot explain the information and the structure without each other. Information is some kind of sequence or pattern of something with a function. And when we are talking for origin of life, information cannot be explained without having some sort of function, and vice versa. The function, when you're talking for origin of life, must be linked to information. Therefore, they are mutually in existence. And of course, there must be a root between those two. Otherwise, there won't be order. Therefore, we can postulate a very clear rule for origin of life. Because during the origin of life, the information, the structure, and the corresponding rule are locked in the origin. When you're looking for origin of life, you must provide some sort of joint mechanism. You cannot take information outside and the structure and function from another side independently. They cannot come independently and just fit each other. Any reliable hypothesis for the origin of life needs to, of course, have to describe a probable information and structure relationships, as I showed you, to explain initial driving selection forces with positive feedback. The positive feedback which I had just talked about. I've seen many hypotheses, and trying to put something simple, and after that they show it more complicated stuff. But there is no explanation of the driving force. What selects for? What is the driving force? Why the more advanced structure will be better than the simple one? What is the force? How it's selected? Without that, there is no very good and reliable hypothesis for origin life. Show me the mechanism of selection. That's important. And of course, how the genetic code comes to be. To answer why the first protein domain is a nucleotide binding. I mean, the data shows that the first domain is a nucleotide binding. You have to provide the way going there. Explain the ribozyme formation, having in mind that the ribozymes, in fact, today are enzymes built up entirely, of course, of RNA. But 99.99% of all the enzymes are proteins. So what and how that's selected? The RNA world is trying to solve that, but I don't think it's a very reliable way. Also, where the energy comes from, it's very common a problem. And much more, of course, you can put more questions to hypothesis for origin of life. Good luck with that. You might do it, you may not. However, it needs answers. That's how and why we have hypotheses. Either those hypotheses explain or do not explain anything. So, let's stop talking to the nature how to make a life. Just think more naturally. So, here I have a representation of short RNAs, just short RNAs. And you can see if you, in solution for example, if you heat the solution, you have a melting process of RNA on the top, and if you drop down the temperature, of course they will hybridize. They will anneal to each other based on the Watson-Crick base pairs. And of course, in this particular environment, some of those might be more stable, some not. Usually the more GC-rich of those RNA will be more stable. Therefore, they will circulate longer in the environment. In these conditions, also based on many papers so far, you can assume processes like template-directed polymerization, non-enzymatic, some kind of recombination between these RNAs. All of that could happen with this RNA. But now, we know that also amino acids will be around. Let's assume also that, that some of those RNA are amino acylated, so that those are linked with the RNA. We just saw the process of amino acylation by the lecturer John Sutherland. So what happened in that process? When you have chilled down the temperature and you have a hybridization moment, annealing moment, because of this hybridization, some of those might stay very close to each other. In order these interactions to be very stable, or to be more stable, you need more hydrogen bonds, of course. That's why the predominantly GC-rich RNA will be more stable. And once they are close to each other, like this, and if you're able to overcome the competing hydrolysis by wet and dry cycle, a peptide bond will be formed. These particular peptides, we call it hybridization-dependent peptides. And pay attention, this is not the peptides which are smashed amino acids to each other without any. This is hybridization-dependent peptides, because it was linked to the RNA. What can you say about the nature of these hybridization peptides? First, they will be not coded. I mean, in fact, there is a statistical probability for every existent amino acids to interact with every RNA. Second, the amino acid composition corresponds to the abundance of those amino acids. And mostly of those peptides, most likely will be alanine and glycine based, because this is the most abundant in all of the experiments and models. When you have synthesized amino acids, the most abundant are alanine and glycine. Some of those hybridization-dependent peptides might incorporate another amino acids, of course, and will interact with RNA. Therefore, will carry on some sort of amino acids like arginine, for example, because arginine is positively charged. It's very well known it interacts with RNA. We just saw the lecture of John Sutherland, and he published some paper, this is a very recent paper of John Sutherland. And he showed, and also today, he showed us the process of amino acylation, but first you have some sort of donor RNA with phospho nitro group linked to amino acid. These interactions, however, this phospho nitro link is on alkali conditions. However, once you go to the acidic conditions, in specific also situation, the bridge is formed, and in acidic conditions, this bond is released, it's hydrolyzed, and voila, we have amino acylated RNA. And this type of amino acylation is very similar to the model today's type of amino acylation. Now, from today's talk, and also John Sutherland provided his talk back in Chicago, we can say that based on these stereochemical interactions, that in some cases, the donor RNA with specific sequence could be transferred. This is the different donor RNAs with the different, happens to be by chance sequences, specifically could transfer the amino acid to another acceptor RNA, which we refer as a proto-tRNA. And what is important is that it's specific to the sequence. So, as John explained this morning, it's happened. So, we have a link between the amino acid and specific sequence of the acceptor RNA. Now, let's try to combine all together. Okay. So let's try to combine all together. So first, we have a donor RNA in alkali conditions. After that, you have this transfer of amino acids as I described and as the John Sutherland provided. Now, we have amino acylated acceptor RNA with, of course, specifically to this particular stereochemical mechanism. And as I explained before, with the up and down of the amino acids of the RNAs, chilling down and also heating the environment, there is a hybridization peptide formation. So So this is kind of a process where you accumulate hybridization-dependent peptides. And now pay attention of this particular moment. Here is the moment. Some of those peptides will start because of the by chance sequence, will start to interact and also bypass the process of amino acylation from the alkali conditions. This is the alkali conditions. And now we have a moment of bypassing this entire process. But how interesting is that? This is a huge selection advantage because now we no longer depend on alkali conditions. Otherwise, it starts to be very complicated. You have some sort of physical separation between these processes in alkaline conditions, in acidic conditions. But because of the bridge peptide, that's how we call the peptide which facilitate this amino acylation, just because of this, now we bypass this particular alkali conditions. And also, you can see how this bridge peptide will start to interact with nucleotides and activated nucleotides with the short RNA, mimicking the donor RNA, which comes from here, and try to transfer and bypass the process of amino acylation. Because of the selection forces, every time when you have better chance to have more fitted to this process peptide, it will grow and will make more advanced form of this peptide and slightly longer advanced form of peptide. And in the future, with many, many generations, after all, those kinds of interaction will make amino acyl synthetase. Those particular protein have a nucleotide binding domain, and we know that very well. At the same time, you will expect co-evolution of the small subunits and the large subunits of RNA. This co-evolution will provide additional moment of independence of wet and dry cycle. Again, we are observing here a huge selection force. That's why it goes in this way. So, if we go back to the same scheme I showed you with the system, where the information comes from. The information comes from the specific stereochemical interaction between amino acid and the RNA. Now we have specificity because only particular RNA will go into the advantage mode. There is a rules between those. The rules could be ended in this case, in the beginning of origin of life. The rules will be Watson-Crick base pairs, and of course some primitive protocodon formation. The structure and the function is provided by hybridization-dependent peptide and the bridge peptide also. But predominantly, if you have a peptide containing arginine, for example, it will stabilize the entire complex, which is another stabilization and another advantage and selection force. Again, this is a published paper from Dr. Lauren Williams. He provided wonderful data for that. And what about the positive feedback? The bridge peptide actually is completely capable to do this positive feedback to the amino acylation process. That's why you have the selection. And fitability is provided by some ribozymes. That's why the ribozymes are selected. So initially, at the very first point, where the energy comes from? Well, that's a long story, but pretty much it comes to the activated nucleotides and activated amino acids. So, for example, David Kettling can answer this question better than me. And of course, that's explained many, many more things which we observed in life. Okay, so we have some sort of build-up hypothesis based on many, many data. Now is the time for experimental research. So nothing in biology makes sense except in the light of evolution. And I will say the same is true for origin of life. Now we have to have a new way of thinking. Before, subconsciously, we think that, okay, origin of life will happen, and after that the evolution will kick out and will continue. This is completely wrong thinking. Because the life and the evolution are the same thing. The beginning of the evolution, the beginning of information selection, is the beginning of life. That's why you have a functional boundary. This is a functional boundary. Although all the polymers interactions might be pretty much the same before and after, functionally, now we have difference. Okay, I would like really to thank the National Science Foundation, to Bulgarian Academy of Science, to University of Buffalo, and also to Anastas Gospodinov. He helped me a lot. Also, I utilized the research from John Sutherland, which he just showed us this morning, his data. Lauren Williams, which is here in the building, Gustavo Honores, Perez Orueda, and team, and many, many more. I simply cannot put the list here of everyone that I used in this work. Thank you.
Some questions? Yes.
Thank you, Dimiter. I understand that your main concern in this talk is actually with the mutually supporting bridge between information and structure. Part of what you said is actually sort of about proposing details of mechanism to make things plausible. I want to make a comment that's more sort of to that mechanistic side, acknowledging that it's not the central part of the here. But it does seem pertinent, maybe to this discussion and also to John's. There's a lot of looking at amino isolation that makes use of base pairing functions of RNA. But Mike Yarris wrote a paper some years ago, I forget it was 2007 or that. It was something like the function of minuscule minuscule encoded RNA or something. And one of the striking things that was reported there was the role of the ribose phosphate platform itself as apparently a mediator for polymerization, in which the growing peptidal chain can hop back and forth between 2' and 3' and stack up on itself as new monomers or editors for like aerosols standing on each other's shoulders. And there has been work by Sofia and Fleet Chan, apologies if I mispronounce the second name, on the role of the activating RNA itself in some amino acid tRNA synthetases in what they call substrate-assisted catalysis, in which the ribose phosphate moiety is essential to producing the transition state to such a degree that the platform of the synthetase is just a kind of tribute trap. So as we think about RNA, it looks like we have at least a few bits of evidence for it as a key enabler of the very earliest transition states, just the ribose phosphate platform as a monomer. So this is much more like the cofactor role than it is like the base pairing role. And I just wanted to have that in the room as a piece of thing for discussion.
Yeah, we'll keep in mind that, and we obviously have to discuss details. Now, of course, as a concept which I provided right now, we don't know lots of details, what actually is very important in the process. Although as concept, there will be surprises. I agree with that.
questions? Yes, down there.
Yeah, hi, this is Warren. I think the way you're thinking about evolution and Darwinian evolution, I just would like you to rethink that. Evolution, in the first place, we are a product of constructive neutral evolution, not Darwinian evolution. The idea that all evolution is Darwinian evolution, I think that's a really pinched view of looking at things. And the idea that Darwinian evolution has to spring up de novo and start going, that's a violation of the continuity principle, and it's just not how any kind of evolution works. And it just seems like you're asking kind of this. I just find this incredibly improbable that these complex chiral molecules just spring up de novo and start base pairing and going on. I mean, there had to be a prior evolutionary process, I would think, that is maybe not Darwinian. And all evolution is not Darwinian evolution. That's I think, that's just a fact. We are the product of non-Darwinian evolution. It's constructive neutral evolution. Evolution evolves. Evolution is not a thing in the way you're describing.
Well, first of all, if you look at the mechanism which I provided, you have to just eliminate all of the kind of attached description by wording. We cannot call it just Darwinian evolution. Darwinian evolution, some people call it when they are talking for much more advanced organisms. That's why I put several names, for example, information-dependent selections. However, the mechanism with the feedback is absolutely realistic. This is how actually by all of mean that evolution works. I don't know another way of doing evolution. It's also, you have to pay attention that nothing can advance without this mechanism. You cannot have something simple and this to try to build up and to make adaptation without those mechanisms. And there's no other way. So if you provide another way, that will be interesting. I would like to hear it. It's wonderful.
Okay, well, it sounds like we'll have to have another meeting at some point to see how this argument evolves in time, whether it's selected or not.
So build up attention here, right? Explode. Okay, we'll have to discuss probably later all of that.
Okay, so discussion can continue over coffee. I think people can come back here about 11:20 or so for the next session. And thank you all for very active, very engaged discussions this morning. And speakers.